Hi. Remember we're talking about problem solving. We talked about when you first solve a problem, what you do is come up with a perspective, a way of representing the set of solutions. Then we talked about how you use heuristics to search among those possible solutions given your representation. And we've seen how having lots of heuristics and diverse heuristics can help you look at more points and possibly find better solutions. What we want to do in this lecture is combine those two ideas, perspectives plus heuristics, to show why teams of people can often find solutions to problems that individuals can't, why teams are better. Now when I say teams, I'm going to use this in a very loose sense. I don't necessarily mean a team of people sitting in a room and brainstorming, that sort of stuff. What I mean is a collection of people, possibly, working even over time. So if you look at something even like the toaster on your counter, you can think of that as being something that's been really consistently and constantly improved upon by a team of people. So it's the person who first invented the toaster, and then somebody improved it, and then somebody came up with the crumb tray, and then somebody came up with the automatic shut-off button, and all sorts of things, right? So a toaster consists of a whole bunch of improvements, and you can think of that as being, that current solution that we have as being something that a team has come up with. So again, by team, I don't necessarily mean a group all working together and, in some unit. I just mean a collection of people. So how does it work? Why are teams and why are groups of people better than individuals? Well, let's go back and let's think about the candy bar example. And remember, I had one landscape, one perspective based on calories, and that had 3 local peaks, right? And let's represent those by A, B, and C. And then I had another landscape that was represented by masticity, and that had 5 peaks, and we can call these, let's call these A, B, D, E, and F. So these are different than the peaks for the caloric landscape, with one exception. Notice for sure that A, which is the best possible point, that has to be a peak in the caloric landscape, and it's also got to be a peak in the masticity landscape, and that's because it's the best possible point. So if it's the best possible point, it's got to be a peak in every landscape. Now we can characterize these problem solvers by their local peaks, by their local optima. So the local optima of the caloric landscape are A, B, and C. The local optima for the masticity landscape are A, B, D, E, and F. And remember, we said the caloric landscape is a better landscape than the masticity landscape because of the fact that it had fewer local optima. So one way to think about how good you are at solving a problem is how many local optima you have given your perspective and your heuristic. Now here we're assuming the heuristic, right, is just hill climbing. Let's go deeper, because that's a fairly crude way of thinking about how good a problem solver is. We can actually take into account the average value of those peaks. So the peaks where people get stuck are A, B, C, D, E, and F, and we can assign a value to each of those. So suppose the value to A is 10, B is 8, and so on. So A is the global optimum, and some of these other peaks aren't so good. What we can do is we can ask, what's the average value of a peak for the caloric problem solver? So the problem solver who thinks in terms of the caloric perspective, they get stuck at A, B, and C. What's the average value? Well, A has a value of 10, B has a value of 8, C has a value of 6. And so we can think of the ability as just the average of those 3 peaks, which is 8. But if I look at the masticity problem solver, they get stuck at A, B, D, E, and F, and those have values 10, 8, 6, 2, and 4, and the average of those is 6. So we can think about the ability of the masticity problem solver as being 6. So not only did the caloric problem solver have fewer local optima, they had higher average values. This is another reason why that person's a better problem solver. Let's think of them now, though, as working as a team. If I think of them working as a team, the caloric problem solver gets stuck at A, B, and C. The masticity problem solver gets stuck at A, B, D, E, and F. Let's suppose first that the caloric problem solver works on the problem first, and she gets stuck at B. She then passes the problem to the masticity problem solver. And the masticity person says, you know what, I can't help you because B looks pretty good to me because B is also a peak for him. Suppose instead, though, that the caloric problem solver gets stuck at C, and she passes C on to the masticity problem solver. And now this masticity person, C, if you notice, isn't anywhere in this list. C isn't a local optima. That means that the masticity person can get from C to some other local optima, and it's got to be one that's better. Why does it have to be better? Because this person's hill climbing, and if he's hill climbing, then he's got to be able to find something that's better than C, and that's going to be either A or B. So the intersection of these local optima, A and B, are the only places where they can get stuck. if, for example, the domesticity person went first and got stuck at E, then the caloric person could take E and get to someplace else, either A, B, or C. If she gets to A or B, the domesticity person's also stuck. If she gets to C, then the domesticity person can then in turn take it up to A or B. So the only places the team can get stuck is A or B. You can make this formula called the intersection property, that the local optima for the team is the intersection of the local optima for the individuals. So if we look at the team, there's only two places the team can get stuck, 10 and 8, and the average value there is 9. So the ability of the team is higher than the ability of either person. And the reason why is because the team's local optima is the intersection of the local optima for the individuals. So the reason why then we see over time products get better, and the reason why we see teams being really innovative, the reason why we see a lot of science being done by teams of people, is because the only place a team can get stuck is where everybody on the team can get stuck. So this very simple model, having perspectives and heuristics, can explain why is it the case that teams are so much better than individuals, and why over time we keep finding better and better solutions to problems. It's not necessarily that we're getting smarter. Now it's true, we are coming up with new ways to represent problems, and we also are coming up with all sorts of new heuristics all the time. We're developing new ways to solve problems all the time. But another thing that's going on is just because of the accumulation of so many different ways of looking at problems and different ways of trying to solve them, that we get the intersection of all those peaks, and that gives us better solutions. So here's the big claim. The team can only get stuck at a solution that's a local optimum for everyone on the team. That means the team has to be better than the people in it. So what we want, right, we want people with different local optima. We want people to get stuck in different places. Well, how do we get it? We know, we've already looked at this twice, right? We looked at it first with respect to perspectives. If we have different perspectives, so if you code it this way and I code it this way, then we're going to get stuck in different places. We also want people with different heuristics. If I look in this direction and this direction, and you look in this direction and this direction, then when we add us together, we look in all four of those directions. So what we want is we want diverse perspectives, and we want diverse heuristics. And that diversity will give us different local optima, and those different local optima will mean that we take the intersections, we end up at better points. That's sort of the big idea. So if we take, again, let's play this out in more details. Again, imagine we've got these, here's this set of solutions. If one of us looks like this, and one of us looks maybe 2 to the left, and one looks 2 down, and one looks to the north, south, east, and west, if we have all these different, maybe one person looks 2 over this way, all these different heuristics, looking at a problem, that means we're less likely to get stuck at the same point, which means the team is going to do better. Or over time, society is going to do better at finding solutions to problems. This all seems really smooth and nice and great, and we've seen teams are better, and we see the value of diverse perspectives, we see the value of diverse heuristics. But what's missing? Because this seems highly stylized. There's 2 things that I've left out. First one is, right, we can write this down as communication. I've assumed that when you've got a team solving a problem, that they can communicate their solutions to one another right away. Now that's not always the case. There's a lot of misunderstanding that's going on, and we might not listen. I might just say, no, I'm not listening, right? And then no matter what you say, we don't find the better solution. Now, if you think of something like the toaster, though, it's weird. We can communicate through the toaster. If I come up with a better toaster and I make it, then you can look at my solution, you know what I've done, and then you can add the crumb tray. So if you think about making an artifact, the artifact itself, if the artifact is the solution, that gets communicated right away. But generally speaking, communication can be a problem. The other thing I've assumed is that there's the possibility of sort of error in interpreting the value of a solution. So I'm assuming if somebody proposes something and it's better, we instantly know it. It's as if there's some sort of oracle we can go to and say, oh, yep, that's a better solution. That may not always be the case. So it could be that I propose something really interesting and people just think, no, that's a bad idea. They make an error in terms of whether or not it's an interesting thing. Or it could be that I propose something that's worse and people think, oh, that's a great idea, and then we actually do it and it's not a good idea. So I've assumed there's no errors in determining the value of a solution, that when somebody proposes a solution, we know exactly what it's worth. That's not always going to be the case. So it won't always be true that there's perfect communication and there's perfect evaluation. So in a richer model, we could include communication error, and that's going to hurt teams. And we can also include just error in evaluation. That's also going to hurt teams. Even so, right, this model's shown us something fairly powerful, which is that diverse representations of problems and diverse ways of coming up with solutions can make teams of people better able at coming up with solutions than individuals. And it also sort of told us where innovation is coming from, right? Innovation is coming from different ways of seeing problems and different ways of finding solutions. There's a lot going on, right? Now I got this model of problem solving, and we can think about people finding solutions to particular problems. Now we want to step back a bit in the next lecture and want to think about, what about bigger things like designing a house, designing a car, designing a railway system, designing a city, bigger problems. Well, oftentimes those bigger problems, the solutions, even think of it like making a computer. A computer may consist of the solutions to a whole bunch of sub-problems. So where we want to go next is we want to talk about how we combine solutions to come up with new solutions. And we'll see how that can even be used as an argument to where economic growth comes from. It actually comes from individual solutions being recombined. Okay, thanks.